Hey guys, so in this lesson we're going to look at stretches, compressions, and reflections and how they affect our sinusoidal functions. So on top of the last lesson we did the phase shift or the horizontal movement, and we also did the vertical movement. But in this one we're going to look at how we can stretch it, compress it, and any reflections that we might have. So the first investigation, I asked you to look at the reflections. So I asked you to graph sine x and y equals minus sine x. So if you went to Desmos, you would have got something like this. This was our sine x. This red one is our original. And this one, this black one, was our negative sine x. So what you should notice is instead of going up to start with, it actually went down, came back up, and then went up. Instead of the original curve that goes up and then back down, this one goes down first and then up. So what the negative sign actually does is reflect it in across the x-axis. So you may have come up here and wrote one goes up, one goes down, something like that. Goes up, the other down. So the summary for this, if you have a negative sine x, the negative tells us we have a reflection. Okay, that one's super easy. So anytime you have a negative sign in the front, you're going to start by going down instead of going up. The second set, I wanted you to look at amplitudes, or in this case, this is our vertical stretch. So let's write this down. Vertical stretches. And then we'll go look at case 1 and case 2, and you can see if you got what I got, and I'll talk about what happens with it. So this here is what you would have got if you had done the sine x, the 2 sine x, 4 sine x, and 8 sine x. So this one here is the sine x. This was the 2 sine x. This was the 4 sine x. And this was the 8 sine x. Now what you should notice is that it didn't change like the points where it actually intersected the graph. So it didn't actually change where we started and where we finished in terms of our graph, but it did change the amplitude. So what happens is this amplitude from here to here, instead of just being 1 like it is in the normal one, this one was 8. And then this one here up to here was 4. This small black one had an amplitude of 2, and then our original had 1. So this number that's out in front actually tells us what our amplitude is, and it tells us how vertically stretched we are. Moving to the other one, this was case 2. This first one here is your regular one. This one was your 1/2, the black line. This inside red one was your 1/4, and the blue one was your 1/8. So the 1/2, 1/4, and 1/8 actually vertically compressed it. So let's go back and we'll kind of give a little bit of a summary up the top for this one. So you'll notice that in case 1, the number tells us our vertical stretch. Which is our amplitude. And then in this case too, it was also our vertical stretch, but in this case it's a vertical compression because it actually like smushed it closer to the x-axis. So our amplitude went down. Now that's because our numbers here were like a half, a quarter, and 1/8. So they just became smaller, so it meant it got closer and closer to the axis. Where in case 1, the numbers got bigger, 2, 4, and then 8, and so it became more stretched out. So in this case, y equals a sine x. This a value tells us our amplitude. Okay, so in this on this second page, we were going to investigate the periods. So I wanted you to graph these following functions. So notice the numbers just in a different place. And then here in case 2, I changed them again to 1/2, 1/4, 1/8. Now, if you did it in Desmos, let's go see what you would have got and compare it with what I. So here's the first example. You'll notice this red one here that I'm kind of going over is our original, where it starts at 0 and ends at 360. Our second one, which was our 2, what it actually did was make it go through 2 cycles. So we actually did 2 cycles within our within the 360. It went from 0 to 180 and then again from 180 to 360. The 4 did the same thing. That's our other red. I'm just going to go over it with green. See, we've got 1, 2, 3, and then 4. So it actually made 4 cycles within the 360. And then the last one, that blue one, you'll notice, or you could probably count them out, there's 8 cycles of it. So that number actually tells us how many periods are within that 360 degrees. And it also will tell us how far those periods are, and I'm going to show you how to do the calculation for that. The second case, which is down here, I did an example of it. It stretched it out. So the one half actually made the sine function. Here it is. It's that black one. It went to 360 here and then went all the way to 720. So it actually took 720 to complete one cycle instead of the 360, and it just stretched out from there. So it actually stretched it out in this case instead of compressing it. Let's go back to the investigation. I'll show you what happens with it and how we can calculate that. So in this case, you should have seen that in case 1, it compressed horizontally. So it actually put more periods or cycles in the 360. And then this one stretched horizontally. So it actually made it take longer to do a full cycle or period. So the periods are longer. And in this case, the period was shorter. And when I say longer and shorter, I mean shorter and longer in terms of 360. Okay, there's a really easy way to calculate exactly how long the period is going to be. And I'm going to tell you that, but notice kx. So k helps tell us our period. Now, let's go down and I'll show you how to calculate it. So from the equation, we can easily find out what our period should be with one small little calculation. And it is this one. The period is 360 divided by k. So if we know what k is, we can figure out how long the period actually is. So in our example, what is the period of the following function? Y equals sine 3x. So I look here and I see that k is equal to 3. So all I'm going to do to find the period is equal to 360 degrees divided by k, which is 3. So in this case, our period is 120. Now, if you graphed this equation into Desmos, you would see that it starts at 0 and comes back to the beginning at 120, and it does another cycle after another 120 to 240 and does another one. So it actually has 3 cycles within 360 degrees. Now, let's do the last example. Given the function y equals 3 cos 2x, we're going to determine the period and amplitude of the function, and we're going to determine the domain and range of the function. So, the 3 is in the A position, which I said was our amplitude. It tells us our amplitude, which means we have a vertical stretch of 3. And the period, k, is equal to 2. So our period equals 360 divided by 2, which is 180. So one whole cycle or one period is 180 degrees. We're going to get 2 cycles within the 360 degrees. Determine the domain and range of the function. Now, what's nice about sinusoidal function is the domain is always the same. X is in the set of real. Always, always, always. It doesn't really change, especially for sine and cosine. But the range is going to change. Now, the range is going to change because in this case, our amplitude goes up to 3 and down to -3. So it's going to stay within those 2 values. So instead of being a max of 1 and a minimum of -1 like it was with our regular sine, this one is going to be y is in the set of real such that y is between -3 and +3. So it's just going to stay between those 2 values. It always stays within the max and min of our amplitude. Okay? Hopefully that helps you complete all the practice stuff. If it doesn't, ask me questions or feel free to look elsewhere. There's lots of stuff on this on the net that I haven't added in the lesson, so you can kind of check it out. All right. Bye, guys.